Hey, time for another lesson on SHM, and this time we are going to be looking at energy in simple harmonic motion, and then we're going to look at something called damping as well, which is very related. So we start off with one of our favourite oscillators, the pendulum. So let's have it oscillating from there, and it goes from its maximum displacement here to its minimum displacement here, back to its maximum displacement in the other direction here. So it was vaguely symmetrical. And sort of following this path as next backwards and forwards. And we're assuming no energy losses so far. So all of the energy in a simple harmonic system, a simple harmonic oscillator, and I suppose in any system really, is made of both kinetic energy and potential energy. So we can write that E total is kinetic energy, EK, plus potential energy, EP. And they're going to be different at different points. So there's the distribution of kinetic energy and potential energy is going to change at various times throughout the oscillation. So if we look at both of them, so let's talk about EK first. So the kinetic energy here and here, so at the maximum and minimum of the oscillation, or the two extremes, is going to be zero. And it's going to be zero there as well. And then here it's going to be at its maximum. The potential energy is going to be at its effectively maximum here and here. And so if the maximum plus zero is your total energy, then the maximum must be equal to E total. So E total goes here, and effectively zero there. Not effectively, actually, I suppose. And therefore this must be E total there as well. So the kinetic energy is zero at the extremes and equivalent to the total amount of energy in the system in the middle, and the potential energy is equivalent to the total amount of energy of the system at the extremes and zero in the middle. Okay? And we can do some nice maths using this relationship to actually derive one of our equations for speed, which we're going to do now. So if you think of the equation for potential energy in a spring, so the potential energy in a spring is E is equal to a half times the spring constant times the extension squared. And if we've got a spring system that's oscillating, then the maximum potential energy is going to be that at the maximum displacement, so a half times k amplitude squared. Now we can rearrange this equation here for EK. So let's do another colour in fact. EK, our kinetic energy, is equal to our total energy, take away our potential energy. And we know that our E total is the same as our maximum EP. So actually this is also equal to E total. So we can put in the kinetic energy of the system, is in fact a half Ka squared minus a half Kx squared by substituting in these two, which we can then factorise into a half Ka squared minus x squared. And we also know another equation for kinetic energy. So kinetic energy is a half mv squared. So a half mv squared is equal to a half Ka squared minus x squared. Do some cancellation. Let's cancel out the halves. So we have mv squared is equal to Ka squared minus x squared. And if we're going to divide both sides by m, to give us v squared is equal to k over m a squared minus x squared, because we've seen k over m, or rather m over k, in one of our other SHM equations. So if we think of the, I don't know what to do, a little aside here, let's say. If we think of the equation for the time period of a mass spring system, we have t is equal to 2 pi root m over k. And if we do a little bit of rearranging of that, we can have root k over m is equal to 2 pi over t. And 2 pi over t we know is omega. Oops, omega, oh yeah. So we can say omega squared is equal to k over m if we just square both sides. So we can substitute that omega into here, or omega squared into here rather. So we have phi squared is equal to omega squared a squared minus x squared. Or if we square root the entire thing, let's just try and fit it in here. At the very bottom, phi equals omega root a squared minus x squared, which is how we normally see it written. So this here is our lovely equation for speed. So if we think about graphing these equations, what are kinetic energy and potential energy going to look like on a graph? Well, we know that kinetic energy is equal to a half mv squared, sorry. And we know that our potential energy is equal to a half kx squared. It doesn't necessarily have to be a spring system, but I think it makes more sense to think of it that way. So if we start drawing a little graph, our potential energy is at its maximum at a displacement of 0. So if we have the displacement axis here, have 0 there, and this can be our energy axis, then our potential energy is going to... Did I use the same colours that time that around? Nope. We had a lovely sort of mulberry pink, didn't we? So our potential energy goes from 0 up to a maximum at maximum displacement. And that actually goes, with this shape here, like a parabola. Let's see how symmetrical I can do this. That could be better. So that E potential is equal to a half kx squared. And then if we are to do our total energy in the whole system, then that's always going to be the same. So this point here is E total. And so to just do that, to take away the curve from E total, will leave us with the kinetic energy, which should give us this shape here. So we should have a lovely sort of two intersecting sections of parabolas here. And the blue value plus the mulberry pink value will always give you E total. Let's just note for the sake of completeness, this is x and this is minus x. Sorry, a and minus a there. So, speaking of energy, as I'm sure you know, 99% of what we do in physics is assuming that energy is constant in the system and isn't being transferred elsewhere. But actually it is, and when we have energy losses in an oscillating system, we can talk about damping. So the oscillations we say are damped, as in they are losing energy over time to whatever. It might be friction, might be air resistance, might be whatever. It might be electric or magnetic work. So, if we do a few graphs here, we can have a look at what damping looks like. So if we do just a graph of displacement against time for an oscillator, and if I do a few of these little, probably not very evenly spaced tick marks just to make life a bit easier for myself. So an undamped system would look like it would be the same size oscillations all the time, always, same period, same amplitude, nothing is changing. Apart from the quality of my drawing, I suppose, but there we go. So this is an undamped oscillations, or free oscillations. So we've got no energy losses whatsoever. But real life, that's not happening. So every oscillation, we're losing a certain fraction of energy from each oscillation. And that tends to be fairly constant. So if we've got something losing a constant amount of itself over time, every set time period, then we have an exponential decay. So if you think of the radioactive decay stuff you've done before, that you lose a set fraction, that half of your isotope every half-life, and you end up with that lovely exponential decay curve. We're going to get a similar type thing here. So if I just once again just draw these in. So we have a nice exponential decay, and that's the maximum energy in the system, which then corresponds to the amplitude. So if we have a nice sort of exponential decay like this, and mirror it underneath the time axis, we rather end up with oscillations that look like this. And it should going very inconsistent with the size. They should still be the same time period. I'm mucking that up there. So we call that damped oscillations, or light damping. And the reason for that is because we talk about heavy damping in a minute. So there's light damping there. We can have something called critical damping. Let's go for another colour here. So critical damping is when we've got enough damping for it to return to equilibrium after just a single oscillation. So if we have, oops, there's our time axis again, and our x-axis. So if we have a single oscillation, first up to maximum amplitude, and then it'll come back down, and then sort of come back to normal without oscillating any further. And we might also have heavy damping, and then heavy damping that doesn't even have a chance to do a single oscillation. So if something's heavily damped, it just does not oscillate at all. So it will be displaced and then go straight back to the centre, to equilibrium. So heavy damping might be it's displaced and then goes straight back to normal. I suppose technically we should be starting these sort of at the maximum amplitude, but it doesn't matter. I've stayed consistent. So those are our types of damping as well. So that's when you obviously don't want things to oscillate forever. You want things like shock absorbers in cars to be damped. So your car, if every time you go over a speed bump, you don't start bouncing up and down forever. Yeah, and they're often used in engineering and things. And okay, so that's it for energy and damping. I've only really got one more thing to cover, I think, in the SHM topic. So that'll be our next video. See you soon.